In this video, we will be talking about potential and kinetic energy. So let's get started immediately. We have four formulas, well, not just four, but these are the three formulas that um, you would want to memorize. So for PE, that stands for potential energy. It is equal to mgh, mass times gravitational acceleration times the height. So the unit for mass is kilograms. The unit for gravitational acceleration will always be meters per second squared. The unit for height is always going to be in meters. And for everything here, for PE, KE, TME, the unit will always be in joules, not Newton meters. Although in theory, joules is equal to Newton meters, since uh, for instance, here for joules, we have kilograms times meters per second squared times meters, or you could just simply state it this way. So this can also be called joules or Newton meters, but for energy, it's going to be joules always, and for torque, that's always going to correspond to the unit Newton meter. So okay, um, for TME, we have PE plus KE. So it's basically the sum of potential and kinetic energy. That is the total mechanical energy, or TME. For KE, uh, it's the same thing as this one for the unit. So we have one half that has no unit, but for mass we have kilograms. For velocity we have meters per second, but we have an exponent 2. So that makes m raised to 2 over s raised to 2, which is the same as this. But for KE, it's 1 half mv raised to 2. For PE, again, it's mgh. Now, regarding the law of conservation of energy, it's strongly associated with TME, such that TME supports this law. So it basically states that energy cannot be created nor destroyed. It can only be transferred into another energy type. So yeah, that's it. That's all I'm gonna say. Um, TME before is equal to TME after. So with respect to what this law states, the energy that is present in the past is also equal to the same energy right now or after. So TME before is equal to TME after. From there, another formula could be derived from it, which is with respect to this one. So TME before can be written as PE before plus KE before. That is equal to TME after, which is, in other words, PE after plus KE after. And from there, another derivation could be drawn from it. So PE, we know that the formula is mgh, and then KE 1 half mv raised to 2. This is all in before, and it's the same thing for after, basically. So um, now that we're finished with our quick rundown on the formulas that will be um, needed in this topic, uh, it's about time that we start understanding these three general statements. So, okay. So for letter A, if the object is at rest, the kinetic energy is at its lowest. So of course, for instance, this is a box. It's sitting on a table, for instance, or a floor. The object is at rest. So kinetic energy pertains to energy with respect to any form of movement or motion. Um, and here, at the same time, the potential energy is at max. It is at its highest level if the object isn't moving or is at rest. So it could be derived from this statement that KE has an inverse relationship with PE. So they cannot be both higher at the same time. One has to be higher and the other has to be lower. So for statement B, if the object is moving at its maximum velocity, so provided that is at its highest, then potential energy will be at its lowest, or 0 joules. So yes, the kinetic energy is at its maximum. So If the object is halfway, then both the P and KE are equal. So that's a possible scenario. So I think for statement A and B, they're logical to understand. But for letter C, it may take some time to understand. Perhaps through some practice questions, it could be understood properly. So let's proceed to number 1. So a 1 kilogram rock is at a height of 100 meters. So the mass is 1 kilogram. The height or the distance, any distance stated, is said to be 100 meters. So what is the rock's gravitational potential energy? What we mean by GPE, or gravitational potential energy, it's just another fancy word of saying potential energy. It's just with the word gravitational, but it's the same thing with PE. So PE is equal to mgh, right? So what do we do now? Well, in the first place, we didn't have to uh, write D. We could have settled with height instead. So yes, everything is good so far. So we substitute the values. So far so good. Based on the calculator, what is the answer? Or yes, this could be answered mentally. 1 times 100 is still the same number, 100 times 9.8, move the decimal place to 2 times to the right. So it is equal to 980 joules. So that is the answer for letter A of number 1. Number 2, so we have to calculate the rock's potential energy at specific distances. Okay, so let's start with, we have to ask first. It's the same scenario with number 1. So the mass is still 1 kilogram. Okay, let's just write it down here again. Okay, for provided that the height is 50 meters, we have to look for the PE, potential energy. So PE is equal to mgh 1 kilogram times 9.8 meters per second squared times the height, which is 50 meters. So 9.8 times 50, that is 490, and then we put joules. This is the answer for the first one. Okay, let's answer provided we have 20 meters. Same mass value, only the distance is different. So here it's the same thing. Just substitute the values. And now we have 196 joules. Okay, next. This might be easy to answer, but eventually in the next questions, maybe in the next lesson, it's not just the PE that we are supposed to find. We have to look for KE, TME, work, momentum, impulse, those values. And it's gonna be kind of complex at first, but eventually you'll get the hang of it as long as you keep practicing and your answers are correct. So yeah, let's enjoy the peace and quiet as of now, because later it's gonna be hellish. So yeah, the process is pretty easy. This is what we're supposed to do if we have to look for PE. But for the other values, I think I want to say this to you now. For PE, you're given a distance. That's the distance that you use. But for other values such as KE, you're given a total distance. For instance here, it's said to be 100 meters. So provided you're given a distance, you subtract it from the total. Did I just say that right? Yeah, basically this is the total, this is the provided distance, and whatever is the outcome or the difference of the two values, that's the distance that you'll be using. For example, here we have 20, so 100 minus 20, you use this distance instead to look for the KE. So yes, that's one thing that makes the future questions later more complicated to answer. Anyways, back to where we are. So we have 9.8 joules. That's for number 3, the third one. Provided the distance is 0 meters, what do? Well, anything multiplied to 0, multiplied by 0, no, multiplied to 0 is going to be 0. So there is no potential energy if the distance covered is equal to 0, or if the distance from the ground is 0 meters. Okay, let's go to number 2. An 800 kilogram car is lifted 10 meters in a service station and therefore has potential energy relative to the floor. If it were lifted twice as high, how much PE would it have? Okay, so PE is missing. We do have the mass. Yes. Let me rewrite the formula for PE. So we put 800, 9.8, and the height, which is 10 meters. So 800 times 9.8 times, wait. Hang on. Sorry, I think there's a mistake with this question. There's a typo. It's supposed to be 20. Since the answer key only states that the distance value is 20. So, yeah. We're gonna use distance 20 instead of 10. So, if we put this in the calculator, the result value will be 156,800. So that's for number 2. Very basic. Okay, number 3. Mass is equal to 60 kilograms. The height is 74.8 meters. How much GPE does the box have at the top of the building? So PE is equal to missing MGH 60 kilograms times 9.8 meters per second squared times the height, which is said to be 74.8 meters. The answer is 43,982.4 joules. Okay, number 7. Mass is equal to 70 kilograms. The velocity is 2 meters per second. Speed or velocity, I remember my teacher saying that they're different in certain ways. I'm just not sure specifically which those ways are. But right now, I don't think it really matters. You can just use the symbol V for the value that's being represented, for the corresponding value that's being represented. So what is his kinetic energy? So right now we have KE that's missing. So again, KE is equal to 1/2 mv raised to 2. 1/2 times the mass, which is 70 kilograms, and the velocity, which is 2 meters per second squared. So 2 raised to 2 is 4. 4 times 7 is Wait, no, no, no. 1/2 times 4 is 2. So 2 times 70, 140. 140 joules. That's our KE. Okay. Maybe number 5 could fit here. I hope so. Okay, so the mass here in this question is 1,400 kilograms. Speed is 25 meters per second. How much KE does the car have? Velocity is 25, right? Okay, so 25 raised to 2. This is gonna... Yeah, let's just use a calculator. So it's equal to 437,500 joules. Okay, that's for number 5. Number 6. Okay, so right now, we ought to look for PE and KE, provided that we have specific height values. But the mass is the same. It's said to be 5 kilograms all throughout. The total H total, let's just say it's H total. Height total is 60 meters. So provided we have 60 meters, let's look for the PE. PE is equal to mgh. Mass is what? 5 kilograms, right? And then we have the gravitational acceleration, which is 9.8 meters per second squared. The height is 60 meters. Again, if we're looking for PE, the given distance is what we're going to use. We don't have to do any extra step. So, hang on. Okay, so 5 times 9.8 times 60, that is 2,940 joules. And let's look for KE this time. So for KE, we're not given a velocity value, right? So yeah, there's gonna be an extra step. First things first, let's write what we have. Yeah, KE is 1/2 mv raised to 2. So let's write 1/2. The mass, which is 5 kilograms. V is missing. So let's look for V first. But we're gonna use kinematic formulas in this scenario. One of them is this. D is equal to VIT plus GT raised to 2 over 2. In fact, that's what we're going to use. So what is the distance that we have? 60, right? So yeah, I don't think we're gonna use what I just said a few minutes ago. Like provided that we have a total distance of 60 and we have a given right now that's 60 minus 60, that's 0. So I don't think we're it's appropriate to apply that right now for some reason. But yeah, the intention for this formula is to look for the time. So I think it's more convenient to substitute first to apply the method for solving literal equations. We all know that the initial velocity, since this ball is being dropped, right, there's no force coming from above. So it's not stated that the person applied force at the beginning of the fall. So it was just dropped. The keyword is dropped. So the VI, it is implied that VI is equal to 0 meters per second. From there, 0 times the time, that's 0. So what we have left is D is equal to GT raised to 2 over 2. Now, let's substitute. 2D is equal to GT raised to 2. T raised to 2 is equal to 2D over G square root. T is equal to square root of 2D over G. Okay, now that we have that, what is our distance again? It's 60, right? It's not 0 in this scenario. G is known to be 9.8 meters per second squared. So what does the calculator say? 120 over 9.8, and the square root is within it. Is applied also in the entire fraction. So the answer is said to be 3.49927 seconds. Wait, this is not the final answer yet, so I'm not allowed to box. But we do have the time already. Let's this time let's look for the final velocity, which is the velocity in the kinetic energy formula. So the V here will always be the VF. So what kinematic formula do we use? We could use this. I think this is the easiest to use. So we know that VI is 0, so we're left with G is equal to VF over T. We're looking for VF, so VF is equal to GT. Now, VF is equal to 9.8 times the time, which is what we solved earlier. It is 3.49927 seconds. So multiply those two values. Our answer is going to be 34.29286 meters per second. Now that we have that VF, let's bring out the formula of KE again. 1/2 mv raised to 2. 1/2 times the mass. Mass is what? 5 kilograms, right? How about the velocity, which is the final velocity? We have 34.29286 meters per second, and we put squared. KE, therefore, is equal to what? It is equal to 2940.00062 J, or joules. If you're wondering why my answer is always with 5 decimals at the right side of the decimal point, that's just the way we put our final answer. It was adopted by our teacher, so yeah, it's a policy. But round it off in a way that your teacher prefers, if he or she has a preference. But yeah, the answer could be a whole number, but for the sake of accuracy, that's the reason why we round off to the nearest 5 digits, just to retain accuracy. That's the main intention. Okay, so given that the distance is 30 meters, let's look for PE. PE, mass is 5, right? 5 kilograms. 9.8 meters per second squared. Height is what? 30. Since we're given 30 this time. So 5 times 9.8 times 30, that is equal to 1,470 joules. Okay, I think it makes sense now. So now that we're given a distance that is lower or less than the total one, So the height total is 60, but we're given a distance of 30. So 60 meters minus 30 meters, the result is 30 meters. And this is the value that we use for looking for the PE. Hence the answer right there. Let's look for the KE value. But before that, of course, you have to look for time. Using the kinematic formula, T is equal to 2D over G. This could actually be a formula that you'd want to memorize so that you don't have to derive every time. I think that's what I did when I took the exam. Distance is what? 30, right? How about the gravitational acceleration? 9.8. The time, therefore, is equal to 2.47, 43, and then 6. Now, let's use this formula to look for the VF. Or yes, we don't have to write that. We could just write the shortcut, the derived version. We know that VI is 0, so we don't add that anymore in the final writing of the formula. 9.8, and the time is 2.47436 seconds. So 9.8 times 2.47436, that is 24. Sorry, no. Hang on. Okay, yeah. This is 24.24871 meters per second. So that's the VF. Jeez, took up so much space. Can we just move it like this? Let's just put a partition. Okay. Now, next we use the KE formula. 1/2 times the mass. Mass is what? 5 kilograms. Velocity, 24.24871 meters per second. So, what's the outcome? KE is 1469.99984 joules, or basically 1470. What was our PE a while ago? 1470. Right now, it's 1469.999, or in other words, 1470. So, based on the values that we so far have in the table, what do you observe? It could be observed that they all amount to... Hang on. Wait. Something's wrong. I knew something was wrong a while ago. Yeah, something was wrong. Yeah, what I said way earlier in this video was right. Exactly right. Very timely. For PE, this is the distance that we use. But for KE, since the H total is 60, the given is 60, so 60m minus the total minus what's being given right now, that amounts to 0 meters. So this is the distance that we use in looking for KE. Where do we use that distance? Here. This is supposed to be 0, and everything here is supposed to be 0. 0 seconds, that means here, gt, g times 0, this is supposed to be equal to 0. And yes, ke therefore is supposed to be 0 too. So this entire thing is supposed to be 0 joules. Now, I think everything is correct now. What can be observed from this table, from the values that we so far have? So again, TME is equal to PE plus KE. So yeah, all of them, this one amounts to 2,940. If you add these two, it's going to amount to the same thing. So yeah, I think those were three statements mentioned a while ago. This one, let's bring this to the table. So yeah, we don't have much space. It's kind of confusing. Anyways, for the first, for statement C in what I'm holding right now, if the object is halfway, then both the P and KE are equal. So that's what's being reflected in the scenario, provided that the height is 30 meters. In the scenario where we have the height as 60 meters, the potential is at its highest, and at the same time, the kinetic is at its lowest, or in other words, 0 joules. So yeah, it's gonna be the reflection of statement B in what we're going to answer next, which is provided that the height is 0 meters. So provided that the distance is 0 meters, PE is missing. 5 kilograms is the mass. Gravitational acceleration is 9.8. How about the height? We just copy. So the answer is 0 joules. As easy as that. Now, we look for KE. So the total, again, is 60 meters. The distance that we're given is 0. So 60, the total minus what's given, which is 0, that's equal to 60. So this is the distance we use in looking for KE through the kinematic formulas. So time is equal to 2D over G. Am I correct? Yes. Okay. Time is equal to 2 times the distance, which is 60 meters. Again, we don't use this one. We divide it by 9.8, or the gravitational acceleration. 120 over 9.8. What is that equal to? You know what? There's another way of solving this. We've been using this kind of method for 2 times already. Let's try this method. So I mentioned earlier about this formula. So potential energy before plus kinetic energy before is equal to potential energy after plus KE after. It's not that I don't want to answer through this method, the one I started with. Let's just try to use this formula for at least one question. So PE before is what? Let's try using this one, the one with 30 meters. So uh, PE before is 1470 joules. And KE before is what? Also 1470 joules. PE after is this one, what we have right now, which is 0 joules. And what we're looking for is the KE after. So basic algebra, it's equal to 2940 joules. That's the answer. We didn't have to go through the kinematic formulas again. That's it for number 6. Number 7. Wait, we don't have number 7. But this is a continuation. Perhaps we'll continue that in the next video. Thanks for watching.